Assalamualaikum warahmatullahi wabarakatuh and good day to everyone. My name is Nurul Afifah binti Zulkifli and I would like to present my final year project, which is identification of vortex-induced vibration in a steam valve system for power generation. First and foremost, I would like to explain a little bit about governor valve. The governor valve is a mechanical valve used in non-electronic hydraulically controlled transmission. Governor valve controls the generator load when the machine is synchronized to the grid because it provides accurate control of steam flow rate entering the turbine. It is usually found in a steam turbine application. There are two types of control valve, which is rotary motion and linear motion valve. Linear motion is the main focus of the study. According to the valve structure, the gas regulator or linear motion valve can be divided into two, which are single-seated and double-seated valve. In terms of design, single-seated valve has a simple and common design, yet it has a good shutoff. The influence of inlet valve pressure of regulator on the outlet pressure is higher than double-seated valve. However, for balancing, it requires more complex design. In a position with the single-seated valve, double-seated valve is heavy and bulky, and from the animation shown below, we can see that the double-seated is way bigger than the single-seated valve. Being in more complex design make double-seated valve to have a good balance force. However, it has a poor shutoff. This is due to the inconsistent in expansion between the core and disc of valve when temperature changes. And it is suitable for the gas pipeline, which gas flow is not always equal to zero. For my project, the problem analyzed is based on the double-seated valve. From the past year, the governor valve keeps showing the failure. After few analyzations made, they found out that the wear and tear of the valve is caused by the excessive vibration. When the vortex shading around the valve is very close to the natural frequency of the valve, it can cause the vibration to occur. Excessive vibration can result in wear and tear of the valve, or in some worst case, it can cause fracture failure. Next video is an example when the vortex shading or the structural frequency is very close to the natural frequency. As you can see, when the frequency of the voice close to the natural frequency of the glass starts to vibrate at a certain frequency. The glass breaks since it is on the same frequency with the voice. And it same goes to the application in governor valve, which I analyzed in this study. Reduce vibration, the effect causing valve vibration due to vortex shading must first be understood. The first step of analysis is to categorize the rotation of the rectangular cage around the stem valve. Therefore, the study aim is to assess the effect of rotation of the rectangular cage around the stem valve to the generation of vortex shading frequency. The study also aims to predict the vortex-induced frequency using CFD. The scope of research are to perform steady and unsteady CFD analysis to determine vortex-induced frequency using the fast Fourier transformation method or power spectral density analysis, and to compare vortex-induced vibration for blockage orientation around the stem valve against its structural natural frequency. From the summary of literature review, I take two journals closest to my study. The first one was from Morita and his colleague in 2007. The title was CFD Simulation and Experiments of Flow Fluctuation Around a Steam Control Valve. And the type of valve was steam turbine inlet valve, and the problem was the valve vibration can cause large fluctuation. The second journal was from Matupriya and his colleague in 2018. The title was Numerical Study of Flow Characteristics Around Confined Cylinder Using Open Form. The problem was there are confinement effect when there is strong interaction between boundary layer, shear layer, and the wake of the cylinder. Here is the methodology approaches using by Morita and his colleague. They use CFD code Matisse turbulence model of large eddy simulation for unsteady flow, LUGSC algorithm, and 3D compressible Navier-Stokes governing equation. And this is methodology approaches used by Matthew Priya and his colleague. They use open form solver with the NS turbulence model. They also use 3 different solvers in their study, which is ICO form, pimple form, and pistol form, with Navier-Stokes governing equation. The open form solver that resolves the governing equation for fluid flow using the finite volume method will be used in present work, considering laminar flow for the steady analysis and K omega model for unsteady analysis to capture the vorticity around the body. This flowchart indicates the proposed methodology in order to achieve the objective of the study. The flowchart consists of the steps that need to be taken in order to retrieve the data to obtain the aim of the study. The turbulent model of K omega is enough to obtain accurate compressor unsteady flow characteristic. The physics of the flow is considered as 2D, transient, incompressible, and turbulent flow. Hence, we choose isoform as the solver for this case by using Piso algorithm to solve continuity and momentum equation has been used. The geometric size of the flow field around a circular cylinder is shown in the figure. To generate the geometry and mesh for this case, we have to specify the vertices, blocks, edges, boundary patches, and merge pair the coordinates of the geometry and also discretization parameters. Left-hand side figures shows the mesh pattern of the case, while in the right-hand side figures show the zoom view of the mesh pattern of the case. The validation of the CFD simulation by comparing the simulation solutions to the previous studies needs to be done before proceeding to the case of the study. To capture the shading correctly, 1000 time step were chosen for the flow past cylinder. Therefore, the time step is equal to 0.01 seconds with Reynolds number of 200. The comparison of the CD and CL values are given in the table, and the solution is converged and yield CD is equal to 1.53. It can be seen that the application of the K omega turbulence model yields good agreements with the previous studies. This is due to the capability of the K omega model to capture the vorticity around the body. In this case, the cylinder is exposed to the transient laminar flow at Reynolds number 200. The computational domain for an inlet was 8.75 times of the circular cylinder diameter, while for the outlet was 10 times the diameter. The weight of the domain was 10.75 times with the diameter, which was shown in the figure, and the diameter used in the study was 4 meter. The airflow is entering from the left side of the valve to the right side of the valve. Figure shows the vorticity magnitude around circular cylinder from time 0 second to 0.5 second. As seen from the figure, as the flow streamed past the cylinder, vortices were formed behind the cylinder. These 6 figures show the formation of the vortices from time 0 second to the time where it reaches the steady state condition. These two figures are the result of the input time history of CL and CD for transient turbulent case simulation at Reynolds number 200 for a circular cylinder. From here, we can see that the time history of CL, which is in the right hand side, grow larger than the time history of CD. A circular cylinder with the same dimension as I mentioned before, together with the rectangular cages with the size of 4 meter weight and a height of 1 meter, which is shown in the figure together with the distance from the center of the cylinder to the rectangular cages and other dimension mentioned in the figure. The figure shows the shading capture for different rectangular cages rotation at t 0.5 second. The time step used is equal to 0.01 second. The case of simulation is a 2-dimensional case for Reynolds number of 200. The input time history of the cylinder at Reynolds number 200 is indicated in the figure. The figure shows that the time history of CL at 0 degree grow larger than the time history of CD, while at 15 degrees, 30 degrees, and 45 degrees show the time history of CD grows larger than the time history of CL. It's like opposite from the 0 degrees. Based on this graph, the plot of the lift coefficient and the drag coefficient against the 400 iteration for all cases means isolated cylinder 0 degree to 45 degree with an interval of 15 degrees. From here, we can conclude that the isolated cylinder takes the fastest time to converge compared with the other cases. The 45 degrees and 0 degrees cases converge at the same time, while 15 degrees and 13 degrees also show the same convergence time. The 15 degrees and 13 degrees cases take faster time to converge compared to the 45 degree and the 0 degree cases. Longer time to converge indicate that the case to reach the steady state is lower compared to the one with the faster time to converge. The power spectral density, or known as PSD, is implemented for array signal processing. Computation of PSD is done directly by the method called FFT, fast Fourier transformation, which apply to calculate the power spectrum as indicated in the figures. The frequency peak at CD occurs at 0.009155 Hz, while the frequency peak at CL occurs at 0.18616 Hz, both at 0 degree rotations. The simulation is conducted for 500 second flow time. The vertical axis indicate both the lift coefficient and the drag coefficients. So the frequency peak at CD occurs at 0.003058 Hz, while the frequency peak at CL occurs at 0.003058 Hz, both at 15 degrees rotation. The value of the frequency in 30 degrees rotation shows the different trend as indicated in both 15 and 0 degrees. The frequency peak at CD occurs at 0.23193 Hz, while the frequency peak at CL occurs at 0.094604 Hz. The power spectral density plots at Reynolds number 200 for 45 degree rotation is shown in the figure. The frequency peak at CD occurs at 0.12817 Hz, whilst the frequency peak at CL occurs at 0.12512 Hz. Figures shows the value of frequency peak at CD and CL for 5 different cases. From here, we can see that the frequency peak at 15 degrees for both CL and CD is the same. In conclusion, from the research of simulation vortex-induced vibration, the investigated effects of flow velocity could be observed from the drag coefficient, lift coefficient, and vorticity magnitude. It could be seen that the orientation blockage around the circular cylinder affects the existence of the vorticity, where the fluid flow past a bluff body creates vortices and was alternately shaped on each side. It could be concluded that the drag coefficient decreased with the increase of orientation blockage around the circular cylinder. From PSD results showed before, we can see that the frequency peak at 15 degrees rotation has the smallest values among all. Last but not least, I would like to sincerely express my gratitude to my supervisor, Dr. Ni Ahmad Ridwan, for the patient guidance, encouragement, advice he has provided. Aerolab UTM for providing access to the high performance facility, and to the Petronas Perhide team for providing technical support. So that's all from me. Thank you.